At 7 minutes past 7 on July 17, 1981, the band on the lobby floor of the Hyatt Regency played to a dense crowd. Thousands of people were in the atrium, and about 60 stood suspended in the air, watching from the walkways. The only warning was a single loud crack echoing through the open volume of the room as the upper walkway visibly shifted. The fourth-floor walkway detached from its suspension rods. As it dropped, it pulled the second-floor walkway hanging beneath it down as well, pancaking several tons of concrete and steel directly onto the dancers on the lobby floor. It took search teams until the next morning to lift the decking off the survivors. The final count was 114 dead and 216 injured. This collapse stands as the deadliest structural failure in U.S. history, the direct outcome of an uncalculated mathematical fuse built into the hotel's structural framework. Within 4 days, the National Bureau of Standards deployed a forensic team to recover the failed connections and reconstruct the exact forces that destroyed the walkways. Their immediate finding revealed a profound structural deficit. The connection that failed never possessed the strength to hold the people standing on it. On opening day, with completely empty walkways, the building was already operating well below code limits. The central mechanics of the failure came down to a seemingly minor field modification during fabrication, a change that bypassed structural review and triggered a fatal load multiplier inside the steel. To understand how the building failed, we must strip away the human tragedy and isolate the strict mathematical statics of a single steel joint. The Hyatt collapse proved that in structural engineering, visual continuity does not equal structural integrity. It is a lesson paid for in lives. The 1978 design by Jack D. Gillum and Associates relied on a specific architectural illusion. The client wanted an open atrium with pedestrian walkways that appeared to float in midair, devoid of vertical support columns reaching the floor. Supporting this illusion required heavy concrete decks built atop long steel box beams running the entire length of the walkways on each side. This diagram illustrates the original intended suspension system. A single, unbroken threaded rod descends from the ceiling truss, passing straight through the fourth-floor beam down to the second-floor beam. The fourth-floor nut resists only its own weight. The second floor's weight bypasses it entirely. Although the two separate loads travel up the exact same piece of steel, they load the rod at two distinct points. At the connection level, the forces remain isolated, but pristine theoretical statics often clash with the heavy physical realities of the factory floor. Havens Steel Company, the fabricator, looked at the prospect of maneuvering a single, continuous cladded rod over 20 feet long and identified a logistical problem. Lowering a massive steel box beam down 20 feet of delicate threads risked scraping and damaging the hardware, making the handling process awkward and expensive. To simplify fabrication, Havens replaced the continuous rod with an offset two-rod system. The upper rod terminates at the fourth floor. A separate lower rod anchors the second floor to that same fourth-floor beam, dumping its force entirely into the upper connection. The math is rigid. The static load pulling against the fourth-floor nut and washer interface was now precisely doubled. From the perspective of a guest standing on the lobby floor, the offset rods appeared identical to the original continuous design. Mechanically, the configuration forced the upper walkway to support the full weight of the lower one. To isolate exactly how that doubled load destroyed the structure, we have to scale down to the architecture of the box beam itself. This cross-section shows the beam was a hollow tube, constructed of two C-shaped steel channels welded toe-to-toe. The hanger rod passed through the flanges. The walkway's weight pulled down on the outer edges, while the nut forcefully pushed upward against the center seam. Forensic investigators found that the longitudinal seam holding those channels together was a partial penetration weld. It lacked the depth required to resist the specific upward tearing action. The most disturbing calculation in Building Science Series 143 proved that even if the original continuous rod design had been built, the weld was so weak it met roughly 30% of the building code. With the offset rods doubling the load, the structural capacity dropped. The fourth-floor connection operated perilously close to failure while holding nothing but its own empty weight. At 19:05 on July 17th, the prying force finally overwhelmed the partial weld. The seam began to peel open along its length, tearing the metal and allowing the heavy steel nut to slip violently upward through the widening gap. The moment the torn flange cleared the nut, the fourth-floor walkway entirely detached from its upper suspension rod, triggering the immediate freefall of both structures. The collapse was the physical conclusion of a mathematical error present in the steel since the day it was installed. Any structural engineer running the new connection through a calculator would have seen the doubled load within minutes. How does a change that creates a fatal load multiplier reach a construction site without a single person running the numbers? In 1979, engineering design relied on multiple handoffs. Detailers drafted drawings, fabricators built components, and the engineer of record calculated loads and formally approved blueprints. Haven Steel proposed the offset rods via an undocumented phone call. A detailer drafted it, assuming someone upstream ran the numbers. When those plans reached the engineer of record, they were stamped routinely. He assumed he was verifying dimensions, not auditing a fatal redesign. They even ignored a severe preceding warning. In October 1979, while the hotel was still under construction, a portion of the atrium roof collapsed. That event should have forced a rigorous audit of all overhead structural connections. No one revisited the walkway joints. In the administrative fallout, the Missouri Engineering Board found the responsible engineers guilty of gross negligence and unprofessional practice, permanently revoking their licenses. The building fell due to a diffusion of responsibility, a workflow where a structural decision was passed down the line without a single person mathematically owning it on paper. When the Hyatt Regency rebuilt its lobby, the fourth-floor walkway was removed completely. The remaining structures used robust vertical columns rooted in the floor. The findings from the National Bureau of Standards forced the American Society of Civil Engineers to rewrite the baseline rules of the industry. The failure of the Hyatt Walkways immediately became the definitive case study in American engineering ethics. The revised Code of Professional Practice instituted an uncompromising rule. The structural engineer of record holds absolute, non-deliverable responsibility for the final structural integrity of the design, including every detail shown in a shop drawing. A formal paper trail is now mandatory. Every field modification, regardless of how minor it appears, must trigger a documented, fresh structural review. The lasting message of Building Science Series 143 is that the gap in diffused responsibility remains invisible right up until the moment it costs lives. In engineering, when a structural change isn't mathematically verified by the engineer, it will eventually be verified